Swayam Prabha. Digital India. Educated India.
We continue with our discussion of modular arithmetic. So by now we have seen quite a few properties. We talked about quotient remainder, GCD, Euclids algorithm, prime factorization, and modular arithmetic, right? Addition, multiplication. And last time we talked about Chinese remainder theorem, which basically tells you that if you have a factorization of m into co-prime factors, possibly prime factors or prime powers, then you could, one way to say that is that there is a CRT representation. So every integer in Zm can be uniquely represented as a tuple of elements in each of the ZAI. Another way to say that is that, and by the way, this is easy to compute using the extended Euclidean algorithm in one direction and by taking remainders in the other direction. And one way to think of Chinese remainder theorem is to say that if you have a clock of m hours, clock with m hours on the dial, and you have in parallel a bunch of clocks with AI hours on the dial, all of them running one step at a time, then by reading the needle positions in the n small clocks, you can uniquely determine the needle position of the big clock. And we talked about multiplicative inverses. In particular, we define Zm star as the set of all congruence classes modulo m, which admit multiplicative inverses, and these correspond to numbers which are co-prime with them. And Zm star has some nice properties. It's closed under multiplication and inversion. And we also talked about Euler's torsion function, which counts the size of, which measures the size of Zm star. And it has a simple formula once you know the prime factorization of m. And Euler's torsion theorem was a very useful, or we'll see, it's a very useful tool to understand how modular exponentiation works. In particular, it says that for any element in Zm star, if you raise it to phi of m, then you get 1 in Zm or in Zm star, right? So the x is in Zm star. And finally, we talked about the cyclic structure of Zp star, where p is a prime number. And we didn't prove this, but it's a very useful property, so you should know about it, that you can generate all the elements in Zp star using some element g, a generator, by simply by taking powers of g, right? So you go g to the power 0, g to the power 1, g square, all the way to g to the p minus 2. Those are p minus 1 elements. They are all the elements of Zp star. So all elements of Zp other than 0. All right, so now we'll try to put these things to use and work out a few examples and consequences of these facts. So let's start by recalling that we define modular exponentiation both in Zm for positive exponents, and we also extended it in Zm star to all integers, right? And the first observation we'll have today is that we define the exponent as an integer, but in Zm star, we might as well think of the integer as the exponent as an element in Z phi m, okay, where phi m is the Euler torsion function. So let's see that it's pretty direct from the Euler torsion function. So Here is a direct consequence of Euler torsion function. So take any element in Zm star and take two exponents. These are integers, but these two integers are congruent to each other modulo phi of m. Okay. Then the claim is that a to the c and a to the d are equal. They're the same element in Zm star. So so why is that? So a to the so we start with Euler's torsion theorem, which says that a to the phi m is equal to 1. Well, that means it's not just a to the phi m, but a to the x for any multiple, x being any multiple of phi m is also equal to 1. But why? Because a to the x is simply a to the phi m times q for some integer q. And so you can write a to the x as a to the phi m the whole to the power q, and a to the phi m itself equals 1. So this is 1 to the power q, so this is 1. All this arithmetic is happening in Zm star. And just to rewrite this, what does it mean for, or rather I'll substitute x as c minus d. So, for any c and d, this is true if c minus d is a multiple of phi m. Okay, then a to the c minus d equals 1. So it's just using x as c minus d. And now what does this say? This says that if c and d are congruent with respect to phi of m, okay, then a to the c minus d equals 1, and I multiply both sides by a to the d, I get a to the c equals a to the d. Okay, so that was my claim here. If c and d are congruent to each other modulo phi m, then a to the c equals a to the d. So another way to state that is we don't really need c and d to be integers. We just need to know what their congruence clause is modulo phi m. That completely determines a to the power c. So we might, or e to the power d, we might as well think of the exponent d as an element in z phi m rather than z itself. Okay, so all of those d's which are congruent to each other modulo phi m, they all give you the same value of a to the d. So often we will go back and forth between the exponent being an element in an integer or an element in z phi m, provided we are talking about the base here is an element in Zm star. Okay, not just Zm, but Zm star. So let's see an application of this, the use case of this. So I can use this to define or find some eth root. So e is some integer, and I'm interested in finding the eth root of an element in Zm star. Where what does eth root mean? So somebody took a number x and did x to the power e. They're asking you to find x. Okay, so you need to find an element x such that when you raise it to the power e, you will get the number you have been given. Well, if I could find a d such that e times d equals 1 in z phi m, right? So if e times d is congruent to 1 modulo phi m, then what this theorem says is that x to the power ed is equals x to the power 1, right? Because ed is congruent to 1 modulo phi m. So x to the power 1 is just x. X to the power ed is, whatever x to the power e that you gave me, I can raise it to the power d and I can retrieve x. So this is a way to solve for the eth root of any given element in Zm star, provided I have such a d such that e times d is 1 in z phi m. Now that may not always exist, so this idea will work only if the e that you gave me does have a multiplicative inverse in z phi m. So e should belong to z phi m star, or in other words, E should be co-prime with them. Okay, so so in these cases, the Eth root is well defined, and I would often just write a to the power 1 over e to denote this, the Eth root for any element e in Zm star. So when I say a to the power 1 over e, the Eth root of a, what I mean is some value b such that when you raise b to the power e, I should get back a. Now this may or may not exist, and when it exists, it need not be unique, right? So that's what we'll see when those things, those conditions will hold. But in general, when I write a to the power 1 over e, you should know that it may or may not exist. Okay, so here is an example. So I started with 9 to the power 10. So this is well defined, no question of that. And I'm interested in this modulo 13. In fact, I wrote this as in Z13 star, which is only to say that my 9 is actually in Z13 star. Okay, so this would be well defined even in Z13. 10 is a positive integer. So let's see. What are we? So you could just go ahead and multiply 9 times 9 and then 9, 9, 9. You can iteratively multiply and get to 9 to the 10. That's pretty inefficient. You could speed it up a little bit by something called repeated squaring, which I'll mention in a bit. But here is a kind of a quick trick in this particular example. So we are working in Z13 star, right? So we might as well work the exponent we could as well consider as in Z513. 513 is 12 here. So the exponent is an element in Z12. Now in Z12, 10 is the same as -2. So instead of something to the power 10, I might as well just look at something to the power -2. This is all well defined. X to the power -2 we have defined as x inverse to the power 2 in Z13 star. Right? So it's all well defined in Z13 star, and since my element 9 is in Z13 star, I can do this. All I need to do now is find 9 inverse and then square it. Now, what is 9 inverse? I can use the extended Euclidean algorithm to quickly compute an integer linear combination of 9 and 13 that equals 1, and that happens to be 9 times 3 plus 13 times -2. So this 27 minus 26 equals 1. Okay, this takes just a couple of steps to get. So what it tells me is that 3 is the multiplicative inverse of 9 modulo 13. So, so in Z13 star, right? So 9 to the 10 is same as 9 to the 9 inverse square. 9 inverse is 3, so 3 square. So happens to be 9 again. So 9 to the 10 is 9 in Z13 star. So along the way, you might have noticed that here this 9 times 3 is 1. So that is actually 3 cubed. So 3 cube is 1 in Z13 star. So now, we also know that 1 cube is 1, right? So if I were to ask you the cube root of 1, then it could be either 1, it could be 3, or it could even be, here's another possibility now in terms of these are the only 3 cube roots of 1, as we shall see later in this video. So, so one cube root is not well defined in Z13 star. Okay, that's an observation here, and that's shouldn't be surprising because 3 and 12 are not co-prime with each other. So what we discussed in the previous slide of taking the Eth root does not apply for e equal to 3 and m equal to 13. How about, say, the fifth root? Well, in this case, yes, 5 and 12 are co-prime, so it is uniquely determined. So all you need to do is go ahead and find out what the multiplicative inverse of 5 is modulo 12. And again, you can do that using the extended Euclidean algorithm. Just takes, again, a couple of steps. And 25 is 24 plus 1. So it's 25 minus 24 is 1. And so 5 inverse is 5. Okay. So that means x to the 1/5 is the same as x to the 5th power in Z13 star. All right, so let's go for a slightly more complicated. So in this previous example, Z13 star, that 13 was a prime. Let's consider something a little more complex. So suppose M is not a prime. M is a product of two numbers, in this case P and Q, which are co-prime with each other. Well, in this case, to kind of break it down into simpler instances, a very useful thing to do is the Chinese remainder theorem. So any element A in Zm, I can write as a pair of elements X and Y in Zp and Zq. So suppose we are given A in Zm, which has X comma Y as the CRT representation with respect to Zp cross Zq. So now let's, what I'm interested in seeing is how exponentiation works, right? Are the exponents modulo something? Let's start with the simple case, the easy case when actually A is in Zm star. And that is to say X is in Zp star and Y is in Zq star. Okay, so everything is nice. So Euler's Torsion theorem does apply here, and just working that out in a little more detail here. So A to the phi m, what is phi m? So since P and Q are co-prime with each other, and we already saw Euler's Torsion function as a multiplicative function, I can write phi m as phi p times phi q. Okay, this follows from the formula of torsion function that we saw. So A to the phi m is A to the phi p times A to the phi q. Now let me look at the CRT representation of this, of A to the phi m. So that'll be equal to just from what we saw about the CRT representation. When you do multiplication, you do coordinators multiplication, and therefore when you do exponentiation, you do coordinators exponentiation, where the exponent is an integer. So the CRT representation of this is simply x and y each raised to the power phi p times phi q. But now this is in Z p star. X is in Zp star, and there's an element in Zp star, and so x to the phi p is 1. That's our Torsion theorem when x is in Zp star. So this means this is 1 to the phi q, so it is 1. And similarly, this is y to the phi q, which is 1 because y is also in Zq star, to the power some integer. So this is also 1. Okay. So nothing surprising here. There's just something you knew from Euler's Torsion theorem, that A to the phi m, we know it's 1, and therefore its CRT representation should be 1, 1. This is when A is in Zm star. Okay, so A to the phi m is 1, and the consequence of that is I could multiply both sides by A, and I get A to the phi m plus 1 is A. Okay. Now, but what if this condition doesn't hold? We'll consider a particularly interesting special case of that, which is suppose the one of them does belong to Zp star. The other one, y, is actually equal to 0, and therefore in particular is not in Zq star. Well, if y equal to 0, still the CRT, it's still true that I can take the CRT representation and multiplication is coordinate wise, exponentiation is coordinate wise. and 0 to the power anything is 0. Anything positive is 0. So in this case, so there's some positive integer, leaving it as it is. Y to the power 0 to the power phi p phi q I rewrote as 0. Now I note that, so this was in ZQ, this was in ZP. Now in ZP, this happens to be in ZP star, right? X is in ZP star. So I can apply the Euler torsion theorem, and just as before, I'll get that it's 1. Okay. So now a to the phi m has the CRT representation 1, 0, which is not the same as 1. So a to the phi m is not equal to 1. Okay. However, if I multiply both sides by a, what do I get? Both sides of this by a. Here it's a to the phi m plus 1. And here it is x times 0. But x comma 0. X comma 0 is the same, was what, the CRT representation of a was, right? Because y was equal to 0. So even though there's not 1, 1, it is such that when I multiply it by a, which happens to be x comma 0, I'll still get back a, right? So multiplying a to the phi m by a, which is a to the phi m plus 1, gives me a. So even though a to the phi m is not identity, this still holds. A to the phi m plus 1 is equal to a in the special case when y equals 0. And symmetrically, when x equal to 0, I get a to the phi m plus 1 is a, right? Now, if these p and q were, say, prime numbers, then this pretty much covers all the cases because ZP star is almost all of ZP except for the element 0, and similarly for ZQ star. So the CRT representation here is an element in ZP, here is an element in ZQ. These three cases cover everything except both of them are 0, but in this case, A is 0 and a to the power any positive integer is 0. So, this property holds in that case, right? I mean, this doesn't hold, but this will. So, in this case, in all cases, right, when m equals p times q, where p and q are primes, distinct primes, you do get that a to the phi m plus 1 equals a. In fact, not just a to the phi m plus 1, I can even have a to some integer multiple of phi m plus 1. Same argument holds. There will be a k hanging around here. And this is not just true for m being a product of two primes. You can inductively argue this holds when m is a product of any number of distinct primes. So there are no prime powers, so I'm not allowing m equal to, say, p square or m equal to p square times q. But as long as m is just a product of a bunch of distinct primes, each raised to the power 1, then you can argue the same property holds. Okay. Okay, so that's, what does that give you? That tells you that even though you cannot take the exponent as modulo phi m, you do get some properties of like if you could work in modulo phi m. So you don't get this property that a to the phi m is same as a to the power 0, right? But you get the property that a to the phi m plus 1 is the same as a to the power 1, or a to the, so a power, anything which is 1 modulo z, 1 modulo phi m is same as a to the power 1. Yeah, so if in particular, if I'm interested in the eth root, right, modulo m, and my base may not be an element, so I'm interested in, say, a to the somebody gave me a to the power e and they want me to solve for a. And a is just an element in Zm, not necessarily in Zm star. And as long as E has a multiplicative inverse in modulo phi m, so actually E is in Z star phi m, then there is a D such that, E times D is of this form, right? So this is just the clock, modulo phi m, where if E and phi m are congruent to each other, there is some number of steps you can take, so D steps you can take, such that you will land at 1 modulo phi m. Okay, so indeed there is a positive integer t such that a to the power ed equals a. So this is something you can do in Z m, for a in Z m, right? So you can find, so what this is saying is that you can find the eth root. So somebody gives you a to the e, you can uniquely find uniquely find a by raising it to the power d, where d is of this form, right? This is so this is saying two things. One is that you raising to the power e is a permutation. It doesn't map two elements to the same element. So it's a one-to-one mapping in Zm, and you can recover this element provided, you can recover this eth root provided you have this kind of a d which is a multiplicative inverse of e in Z phi m star, which you can find efficiently again if you know phi m. Okay, so we'll talk about efficiency a little later, but this is it's well defined. Eth root is well defined for all elements in Zm, provided m is a product of distinct primes and e is co-prime with phi m. So here's another example. So does is there a cube root of 15 in Z33, right? So note that 15 is not in Z star 33. 15 has a common device and non-trivial common device, and nearly 3 with 33. So 15 is is not in Z33 star. So we cannot use our previous observations, but first let's ask, is E the exponent 3 in this case that I'm interested in, does it admit 1 by E, right? So in Z phi 33, is there a 1 by 3? Well, the answer is yes, because phi 33 is 33 is 3 times 11, so it's phi 3 times phi 11. This is 2, this is 10, so it's 20, and 3 is co-prime with 20. So indeed 3 has a multiplicative inverse and happens to be 7, right? So 3 times 7 is 21, so 3 inverse is 7 in Z star 20. However, as I was saying, you cannot apply the Euler's torsion theorem directly, because 15 is not in Z33 star. However, from what I just now described in the previous slide, 33 is a product of two prime numbers and no squares involved here. So I can actually write 15 to the 1/3 as 15 to the 7. Okay. And okay, so this is a good point to actually tell you, how do you compute 15 to the 7? Well, in this case, it may not be all that hard. You just repeatedly multiply by 15, 15 to itself, and you will get, and at each after each multiplication, you reduce it modulo 33. Okay, that's one way to get 15 to the 7. However, if this exponent 7 is to get much larger, this would be rather inefficient, and you can speed things up by something called repeated squaring. So in repeated squaring, what you do is you take 15, then you compute 15 square, which happens to be something, modulo 33 here. And then instead of multiplying 15 to it, you just square this whole thing again. So you get 15 to the power 4. Okay? And you could keep going. You could get 15 to the power 8, 15 to the power 16, and so forth. And very quickly, you can compute 15 to the power, some large integers by repeated squaring. In this particular example, we are not interested in very large exponents, just 15 to the power 7. So we will not go ahead and compute 15 to the power 8. We already have enough to now put them together as 15 to the power 7. So 7 is, if you write the binary expansion of 7, it is 1 plus 2 plus 4. And we already have 15 to the power 1, 15 to the power 2, and 15 to the power 4. So you just multiply them together. So it's a little bit of calculation, and you can trust me, it comes out to 27 modulo 33. Now, if you're not very comfortable just trusting me, and you don't have the patience to carefully check it, here is a simpler explanation of why it is 27, which is something you can verify just by looking at it. So remember, Z33, as a CRT representation, modulo 3 and modulo 11, right? So I can take this number 15 in Z33, modulo 3 it is 0, and modulo 11 it is 4. And now I have to raise this to the power 7. So 0 to the power 7 is now conveniently 0. It's 4 to the power 7 modulo 11 that I'm interested in. And so since 11 is a prime, so 4 is in Z11 star, and now I can use, I can work, I can use Euler's Torsion Theorem. The exponent I can take as in Z phi m. So 4 to the power 7 is the same as, so phi m here, or the modulus here is 11. So the phi 11 is 10. So the exponents are working modulo 10, right? In Z11 star, the exponents are working modulo 10. So 4 to the power 7 is the same as 4 to the power minus 3. 4 to the power minus 1 is 3, and that you can easily verify because 3 times 4 is 12, which is 1 modulo 11. So it is 4 to the power minus 3 is 3 to the power 3, and that is 27, which is 22 plus 5. So this is, 5. 4 to the power 7 is 5. And from the 0, 5, you need to go back to some number modulo 33. We have seen how you can do that using extended Euclidean algorithm, or in this case, you can quickly verify the solution because you take 27 and it is 0 mod 3 and 5 mod 11. Okay, so yeah, so that's the easy way to check this solution, same solution in this case. Okay, so we saw 15 has a cube root in Z33. Does it have a square root? And again, okay, so this time, so 15 is not in Z33 star, but that turns out to be not a problem because 33 is the product of two prime numbers. But how about 2? So is there a 1 by 2? Is there a multiplicative inverse of 2 in modulo of phi of 33? And phi of 33 we saw is 20. So that's an even number. So this GCD is actually 2. So there is no 1 by 2 in Z phi of 33. Okay. So does that mean 15 doesn't have a square root? Well, you can't be so sure. In fact, here is a square root of 15. So I take a number 9. I try 9 squared, which is 81, modulo 33, so 81 is 66 plus 15. So indeed 9 square is 15. So 15 does have a square root. So what does it, why was it not a problem that 2 doesn't have a multiplicative inverse modulo 20? Well, if what it says is that not every number is going to have a square root. Of course, there will be some numbers which have square roots, namely numbers that you obtain by actually squaring things. They will have square roots. Okay, so in particular, 15 does have a square root. But actually, it's not just 9 that is a square root. There's another square root, and you can quickly see that. One way to see that is by doing, trying to find the square root using CRT. So 15 was 0, 4, and when you want to do square root, you need to take square root in each coordinate. So 0 square root is 0. Square root of 4, it does exist, but there are 2 of them. It could be plus or minus 2. Square root of 0 was unique, modulo 3. But square root of 0 can be plus 2 or square root of 4. Sorry, a modulo 11 can be plus 2 or minus 2, and we'll see in a bit that those are the only ones. So there are 2 possible values, and so minus 2 means 9. So if it is 0, 9, then 9 is a solution, and when it is 0, 2, 24 is a solution. Okay. In fact, 24 is minus 9, because 24 plus 9 is 33. Okay, so at least there are, these 2 solutions, and if you trust me, the square root of 4, there are only 2 solutions, then these are the only 2 solutions. Okay, so how do we understand, when you have square roots, or more generally eth roots, even though E may not, be co-prime with phi of 33 or phi of m, where m is a product of distinct primes. So let's take a closer look at this. So as we just now saw in that example, squaring is not necessarily an invertible operation. In fact, that holds true modulo any m greater than 2. M equal to 2 is not very interesting. There are only 2 numbers there, 0 and 1, and they're both squares of squares and square roots of themselves, and there are no other numbers to go around. But for m greater than 2, you will always find some numbers which have which do not have square roots. Okay, so let's see why. So well, okay, so one reason for that is from what we already saw. The when you would have unique square roots is when the exponent is co-prime with phi m, and as we shall see in a bit, otherwise it's not going to be unique. Okay, and for every m greater than 2, I'm claiming that phi of m is even. That's what the statement says. Phi of m is even, and this is something you should verify yourself, and easily do that from the formula for phi of m. Okay, here is another reason to convince yourself that squaring is not an invertible operation. If I took a number and squared it, or took its negative and squared it, they both give you the same value, which means that square, a square, has 2 square roots, a and minus a. And a and minus a might actually be distinct numbers. In fact, m equal to 2 was one case where, for all a and minus a are the same. But in general, a and minus a will be different. Okay, except for a couple of up to 2 counterexamples. So this would be saying that there are some numbers which have at least 2 square roots. Okay. On the other hand, every element has exactly 1 square. Okay, so every element provides you only with 1 square, but some of those squares have multiple elements giving them as a squares, which means there will be some elements which do not have anybody yielding them as a square. Okay, so there will be many elements that do not have any square roots, because there are only, m numbers that are yielding squares, but some of them are giving you the same square. So you do not have m distinct squares you're obtaining. So which means there are some numbers which are not squares of any numbers. Okay, they do not have any square roots. Okay, so there is a name we give for the elements that are lucky enough to have square roots. They are called quadratic residues. So they're basically quadratic numbers, right? They're squares of something. Since we are working modulo, some integer, they're called residues. So these are the residues or the remainders when you divide by that number. So the technical term for them is quadratic residues. They just mean perfect squares, modulo some integer. Okay. So say we are working modulo m, we could talk about quadratic residues. We could talk about quadratic residues in Zm or Zm star. As we'll see, we'll talk more about quadratic residues in Zm star. So I've defined it that way here, but you could define it for Zm as well. So elements which are of the form x squared. Okay, so let's actually look at the simplest of cases where that modulus is a prime number. Okay, so I'm going to look at squares in Zp star. Again, as I said, you could have looked at Zp, but in this case, the only missing element is 0, and 0 is a square root of itself, and no other element is square root of 0. So we'll just ignore 0, and what we are left with here is Zp star, or the non-zero elements. So 1, 2, 3 up to p minus 1 in Zp. And here is a simple example, Z11 star. I've listed the 10 integers there in some somewhat strange order, but this actually is the order in which they are generated by a generator 7. So this is actually 1 times 7. This is 7 square. 7 square is 49, which is 44 plus 5. And then this is 5 times 7 is 35, which is 33 plus 2, and so forth. Okay, so this order, this is just a convenient way of looking at them. Since we know we can do that, I'm just listing it in that order. Okay, so in this picture then, the quadratic residues are, so something like 5 here is 7 square. 3 here is 7 to the power 4, which means it is 7 square. 4 here is 7 to the power 6, which means it is 7 cubed square. So these are all the quadratic residues are all the even powers. So the ones that I skip the odd powers, and what I'm left with are the even powers, and they are the quadratic residues modulo p. And what that tells you is that exactly half of them are quadratic residues. So at least these, half of these are quadratic residues. And since we know that every element, so let me tell you, we'll go ahead and see, what those elements are. So these I'll call QRP star for quadratic residues modulo P. So it's a subset of ZP star, so I call them QRP star. And okay, so let's see, which are the elements in QRP star? So given an element Z, can I check if Z is in QRP star? Well, okay, so one way to do that is pick an arbitrary generator, and so I'm calling it a bad idea here. Pick some generator, and find out the discrete log of z with respect to g. Okay, so to find out whether it appears in an odd position or an even position here. Okay, and if it is even, you know it's a quadratic residue, and you can convince yourself, maybe once after this discussion we are going to have, you can convince yourself that that doesn't matter which generator I pick. If it's odd with respect to some generator, it will be odd with respect to all generators. If it's even with respect to some generator, it will be even with respect to all generators. And if it is a perfect square, then it has to be even with respect to all generators. All right. So if I pick some generator and see that the discrete log is odd, then I know that it is not a perfect square. It's not a quadratic residue. Why is this a bad idea? It's perfectly legitimate. It's correct. The problem is that for large numbers, large p here, it's pretty difficult to compute this discrete log. Okay? So this is not the most efficient way to do this. And again, we'll talk about in the next video issues of computational efficiency. So for now, you can trust me that there's an impossibly hard task as far as we know. But here is a very quick way to do it. And that is by not taking discrete logs, but using exponentiation. So you take your number z and exponentiate it to this integer. What's this integer? P minus 1 over 2. So P minus 1, P is an odd prime. So we are not interested in P equal to 2. Right? So P is an odd prime, and therefore this is a valid integer. And I'm going to check if z to this integer is 1. So the claim is this is 1 if and only if z is a perfect square. Okay, so let's see. So suppose z is a perfect square, then it is some number to the power 2, and that some number can be generated as g to the k for some k. So z is of the form g to the power 2k, and if z is g to the 2k, then z to the p minus 1 over 2 is g to the k times p minus 1. Right? The 2k and the p minus 1 over 2 multiply to give you a multiple of p minus 1. Since g to the p minus 1 is 1, this is just 1. Okay, so that's Fermat's little theorem, or Euler's torsion theorem for p being a prime. So g to the p minus 1 is 1, so 1 to the power k is 1. So if z is a quadratic residue, then this condition holds. Conversely, if z is not a quadratic residue, namely it is an odd power of some generator, and I told you should check that if it's odd power of some generators, and it's not a quadratic residue. So in this case, z to the p minus 1 over 2 is by substituting z as g to the 2k plus 1. This is what I get. I'll still get the 2k part giving me a k times p minus 1. Plus, I'll be left with this, right? So this part, g to the k times p minus 1 goes to 1. So I'm left with g to the p minus 1 over 2, okay? And g to the p minus 1 over 2 is halfway around this clock, and it cannot be 1 because g is a generator means it can become a 1 only after it sees everything. So g to the p minus 1 over 2 is not 1, okay? So just by checking this, I will figure out if z is a quadratic residue or not. And this is where repeated squaring is useful. If p is a very large prime number, you can compute this much more quickly using the binary representation of p and finding z to various powers of 2 and then multiplying some of them together. Okay, so now that we know, a way to see what is a quadratic residue, let's ask, given a quadratic residue, what does its square roots look like? Okay, So let's first start for a simple case, 1. 1 is a quadratic residue because 1 square is 1. What are all the square roots of 1? Okay, so let's actually do this with some algebra. So x square equal to, I'm trying to solve for this equation, right? For x in this equation. I want to find all x such that x square equal to 1. Well, if x square has to be equal to 1, then x plus, there's x square minus 1 equal to 0. X square minus 1 is the same as x plus 1 times x minus 1. This is just, I'm using, the standard distributive property and associativity and commutativity of the arithmetic operations to say that x square minus 1 factorizes as x plus 1 times x minus 1. Okay, and this holds if and only if either x plus 1 equal to 0 or x minus 1 equal to 0. So why is that? So remember, these are both elements in ZP, right? And in ZP, if say both of them are non-zero, then these are both then elements in ZP star, and their product will be an element in ZP star, and that cannot be 0. So if, or another way to think about this is using Euclide's lemma, modulo P, what is this saying? They're a product of two numbers, which is a multiple of P, or P divides the product of two numbers, so it must divide either this number or that number, right? So it's either x plus, so we are relying on P being a prime, right? So either x plus 1 equal to 0 or x minus 1 equal to 0. And of course, or both, but in this case, that's not going to happen for P larger than 2. Okay, so one of these two should hold, means x is equal to 1 or x is equal to minus 1. Okay, they're exactly the same conditions. Okay, so x square equal to 1 if and only if x equal to 1 or x equal to minus 1, or in other words, square root of 1 is plus or minus 1. And these are two distinct numbers except when p equal to 2, in which case they are the same number. So for p greater than 2, there are exactly 2 square roots of 1. And the plus 1 is g to the, 0. Minus 1 is this number g to the p minus 1 over 2. The 10 that you see here, halfway around this clock, is minus 1. Right? So modulo 11 indeed 10 is minus 1. And that's not a coincidence, because halfway around this clock, g to the p minus 1 over 2 is a square root, has to be a square root, because when you square it, you get back 1. So it is a square root of 1, and it is not 1 itself, so it has to be minus 1. Okay. So we already saw it's not 1 itself because g is a generator. It cannot just get to 1 after p minus 1 over 2 steps. So, okay, so those are the 2 square roots of 1. And more generally, the square roots of any quadratic residue, they come in pairs. They're always plus 1, plus, a and minus a, if you're looking at the square roots of a square. And how do you prove this? It's exactly the same argument. You could do the same argument if you want. Instead of 1 here, just put a square, and this factor, the rest of the argument goes as before, and you get x equal to a or minus a. Okay, I'll leave you with an exercise. What if instead of 2 you are interested in some other integer e, and here is a claim you can prove. That the eth roots of 1, there are exactly as many eth roots of 1 as the GCD between e and p minus 1. In particular, if this GCD is 1, this is unique. So there's a thing we already talked about. But when it is not unique, this is a number of distinct eth roots of 1 that you'll get. And you can prove this by considering what's happening modulo p minus 1 in the exponent. Okay. All right, so so that is that's for 1. Actually, it extends to any eth power. Okay, just like it extended to every quadratic residue here, it extends to every eth power also, that there are exactly that many quadratic, or rather the eth roots, as there are eth roots for 1. Okay. All right. So so now that we talked about zp star, that not everything is a square root, only half of them are those even positions in that cycle. Let's just focus on that. Okay, so let's just focus on these elements here, which do have square roots, and we know they all have exactly 2 square roots. Let's yeah, so they all have, so x square is an element in QRP star, and its square roots are plus or minus x. And let's ask, these square roots themselves may or may not be in QRP star. They may or may not have square roots themselves. So if you want to just focus on QRP star, you would be interested in seeing how many of them stay in QRP star and how many of them go into ZP star outside of QRP star. Okay, so let's take a look at this. So the simple answer is that it depends on P. So let's see. So so here, if you look at every element 7, its negative is 6. It's across the so 1, the opposite end of 1 is 10. That's what you get when you multiply by minus 1. When you multiply by minus 1, you go halfway around in this clock. So if you multiply 5 by minus 1, you get to 6, because 5 plus 6 is 11, and so forth, right? So what you're seeing here in the second half of the clock is the negatives of the first half. And in this clock, if you look at it, only one of them, of this 5 and 6, is a quadratic residue, and the other is not. However, if I took my, instead of Z11 star, if I looked at Z13 star, 13 is also a prime. In this case, this is what the quadratic residues look like, right? The, this hexagon that you see here. And interestingly enough, minus 1 is a perfect square. Minus 1, in fact, the QR13 star consists of 3 numbers and their negatives. Okay, so here, when you have, if I took an x square, so I took an element in QR13 star, looked at its square roots, both its square roots would necessarily be in QR13 star. Okay, so yeah, so you have within QR13 star, these elements 1, 3, and 4, they have 2 square roots. Minus 1, minus 3, and minus 4, minus 1, minus 3, and 4. They do have square roots, that's why they are in QR13 star, but their square roots do not lie. Both their square roots are outside of QR13 star. Okay. All right, so the reason for this is, well, it all depends on whether minus 1 is, so when you go across, halfway across the cycle, whether you change your membership in QRP star or not. Okay, so in the case of P equal to 13, if you started off in an element in QRP star and you go to minus QRP, minus that element, you'll still be in QRP star. And otherwise, if you start off outside, then you stay outside, right? So that all depends on whether minus 1 is in QR13 star or not. And when does minus 1 become an element of QRP star? Well, exactly when, the P minus 1 over 2 here is even. So in this case, P minus 1 over 2, so that is 5, and that's odd. And that's why, you skip 5, right? You are here at G to the 4 and G to the 6. So G to the 5 you skip. Whereas here, this is G to the 6. So it is part of the minus 1 is part of QRP star, and that depends on whether P minus 1 over 2 is even or odd. So P minus 1 is even because P is an odd prime. P minus 1 over 2 can be odd or even. And depending on that, QRP star may have all its square roots living in QRP star, or only half of them will have square roots in QRP star. Okay. Yeah, so this turns out to be a nice and simple case that is useful in some applications, that you would work with a QR with a P such that P minus 1 over 2 is odd. So P is prime and P minus 1 over 2 is odd. So that QRP star, within QRP star, square roots are unique. Okay, every element has a square root and it is unique, which means squaring is a permutation. You can invert squares uniquely. Okay, so yeah, squaring is a permutation in QRP star. And you could work out, in this case of examples, so phi square is 25, which is 3, and then 3 square is 9, and so forth. So you'll see that when you take squares, you stay within this set of 1, 5, 3, 4, and 9. All right, so yeah, so to conclude, in ZP star, if P minus 1 over 2 is odd, then squaring is a permutation. And it's also easy to compute. The square is of course easy to compute. Square root is also easy to compute, and that's because you can raise a number to P plus 1 over 4, and I'm claiming that that's a square root. Why? First of all, this P plus 1 over 4 is an integer, and that's because P minus 1 over 2 is odd. So you add 1 to it, what you'll get is P plus 1 over 2. So P plus 1 over 2 is even. So P plus 1 over 4 is an integer, and QRP star is closed under multiplication. So you would get this element is in QRP star. On the other hand, if I did a square of this, I will get z to the P plus 1 over 2, sorry. And you can verify that that's equal to z. Okay, so yeah, that I'll leave that as an exercise. So to summarize, for every, so this was what we started with today, the Euler Torsion Theorem, and this is stated for Zm star, and that means in Zm star the exponent could be thought of as modulo Z phi m, and in particular you could even do, whenever you have an exponent which has a multiplicative inverse in Z phi m, you could find the eth root. Now, you could, while this is not true anymore for all elements in Z phi m, for m which is a product of distinct primes, something similar is still true. That is a to the phi m plus 1 equals a, and that, yeah, so in this case a to the phi m need not be 1 for many a's. However, this is still useful enough to find the eth root, provided E is co-prime with phi m. Now that argument excludes the case of E equal to 2 because phi m is even, so E equal to 2 will not satisfy this condition. So we looked at that separately, and I mean, as one of the interesting examples where this doesn't apply. And we looked at ZP star mainly, and where P is a prime, and every element has two square roots. Every element which has a square root has two square roots, and if the prime P has a special property, namely P minus 1 over 2 is odd, then actually within the set of quadratic residues, there is only one square root.